Hello viewers, welcome to this lesson of learning. In the previous presentation, you had seen the concept and servicing of the interrupts along with the interrupt driven data transfer techniques. In addition, you had seen the various types of interrupts, their priorities and the polling techniques used for the identification of the interrupting devices. In addition, also you had seen the interrupt system of 8085A. In this presentation, we shall be learning the handling of the multiple interrupts, the nesting of the interrupts and the details of the interrupt controller 8259A. To review, any microprocessor may have general purpose interrupts and the dedicated interrupts. To see the dedicated interrupts, in schematic A, devices D1, D2, D3, D4 etc. each has a dedicated line of the microprocessor onto which it can send the request. On receiving the requests from the interrupting devices, the microprocessor identifies the device according to the priorities of the interrupts. Once it identifies the interrupt to be serviced, it automatically generates the address vector of the interrupt service routine corresponding to the interrupt, which is already placed at a known location of the memory and starts servicing it. No additional extra hardware is required for this purpose. It is very simple to service such interrupts dedicated each one for each device. But that facility cannot be offered to several devices because of the limitations of the number of pins on a microprocessor. For that matter, the alternative can be that we can have a general purpose interrupt like int5. In this case, several devices like D1, D2, D3 up to say Dn can interrupt the microprocessor through such general purpose interrupt int5. Now, in that case, the microprocessor has to poll for identification of the devices those are interrupting and finally to select the device to be serviced through the external hardware. After identification of the device to be serviced, the microprocessor then seeks the corresponding call instruction from the device so that it can identify the interrupt service routine. Then the microprocessor of course branches to the required interrupt service routine and services the interrupt. In case of 8085, the dedicated interrupts have the correspondence in trap, RST 7.5, RST 6.5, RST 5.5 and the general purpose interrupt is INTR. Now, while routinely running its program, the microprocessor has its interrupt system enabled. When the interrupt system of the microprocessor is enabled, if any interrupt happens to come, then the microprocessor suspends the routine execution of the program and it branches to the corresponding interrupt service routine to serve the interrupt. As soon as the microprocessor enters the interrupt service routine, the interrupt system of the microprocessor is disabled automatically. Then during the servicing of ISR, the microprocessor is not interrupted, of course with the exception of non-maskable interrupt. Then near the end of the servicing of the interrupt service routine, the interrupt system of the microprocessor is again enabled by execution of some instruction like enable interrupts. Then the microprocessor goes back to take up the execution of the routine program. Again, if any other interrupt happens to come, that will be serviced accordingly. This process goes on. But there can be a changed situation. In that case, suppose the microprocessor is running its main program and its interrupt system is enabled. Say if any interrupt comes now, then the microprocessor will automatically branch to its corresponding interrupt service routine, say ISR1. The interrupt system of the microprocessor is automatically disabled. Now, if by the execution of some instruction like enable interrupts, if we enable the interrupt system of the microprocessor during the execution of ISR1, then the microprocessor is capable of entertaining other interrupts. Now, if another interrupt comes and that may be of lower priority compared to the one that was being serviced, the microprocessor will suspend the service of the earlier interrupt and will branch to the second subroutine, say ISR2, to serve the later interrupt. After completion of the service of the second interrupt, it will go back to serve the earlier interrupt, then completing the service of this, it will go back to the main program. This process of interrupts services is called nesting of the interrupts. The nesting of the interrupts can be carried to several levels. So, we have seen the handling of the multiple interrupts in this case and the nesting of the interrupts, but we have seen that while servicing the multiple interrupts through a general purpose interrupt, we require the external hardware for polling of the identification of the interrupting device to be serviced, and in addition every device has to have a hardware to pass the corresponding call instruction and the address vector of the interrupt service routine. Now, if this facility is provided to several devices, then the chip count of the system will increase, thereby the cost of the system will increase. So, the alternative is to use the dedicated programmable chips, that is programmable interrupt controllers. 8259A from Intel is one such chip. Now, this chip is a 28-pin chip. It is capable of handling 8 interrupts when used singly. Of course, this interrupt facility can be extended up to 64 interrupts by cascading these chips in the master slave configuration. This chip also is capable of being interfaced with 8-bit microprocessors like 8085 and 16-bit microprocessors like 8086. Let us see the main features of this controller. This controller can provide the priority assignment up to 8 interrupt requests. The supply of the address vector of the concerned ISR is given by this. The ISRs can be placed anywhere in the memory space. The individual interrupts can be masked. The status of the pending interrupts, the in-service interrupts, which can be more than one in case of nesting, and the masked interrupts can be read as the status of the controller. The interrupts can be set up as level interrupts or they can be edge triggered interrupts. The priorities of the interrupts can be dynamically changed during the execution of the program. Let us see the operation of this controller through its block diagram. This controller has 3 8-bit registers: interrupt request register IRR, interrupt mask register IMR, and in-service register ISR. In addition, it has the blocks priority resolver, the control logic, the data bus buffer, the read write logic, and the cascade buffer oblique comparator. Now, whenever the interrupts occur on the interrupt input lines IR0 to IR7, they are stored in the IRR register. The priority resolver, on reading the information of IRR, IMR, and ISR, resolves as to which interrupt has to be serviced next, and it generates an external interrupt through int line through the control logic block. This int line is connected to the general purpose interrupt of the microprocessor INTR. On recognizing this general purpose interrupt, the microprocessor acknowledges it back through its interrupt acknowledge line INTA bar. On receiving this acknowledgement, the controller sets the corresponding bit of the interrupt in the in service register and resets the corresponding bit in the IRR, thereby marking the beginning of the service of the interrupt. Simultaneously, it sends the operation code of the call instruction to the system through the data bus buffer. On receiving the operation code of the call instruction, the microprocessor sends two subsequent acknowledgements to the controller, thereby asking for the address vector of the interrupt service routine. The controller responds by sending the lower and higher byte of the address to the microprocessor, and correspondingly the microprocessor then branches to the required interrupt service routine servicing the interrupt. The data bus buffer interfaces the internal bus of the controller with the system data bus. The read write logic has its inputs as RD bar and WR bar, which receive their control signals from the system read and write control logic. The A0 of the read write logic is connected to A0 of the address bus of the system. The rest of the these bits of the address are decoded by the address decoder, and the output of the address decoder is connected to the CS line of the controller. Thus, CS and A0, they determine the addresses of the internal ports of the controller. We have seen that the interrupt facility can be extended up to 64 interrupts by cascading such several chips in the master slave configuration. When cascaded in the master slave configuration, a maximum of 8 slaves can be configured with the master. The output from each of the slaves is connected to one of the interrupt input lines of the master. When the master has to address a slave, it sends a 3-bit address through CS lines CS0, CS1 and CS2. Correspondingly, the slave receives this 3-bit address through the corresponding CS lines. The logic on SPEN line defines the role of the controller, whether it is a master or it is a slave. A logic level 1 on SPEN line defines the controller as a master. A logic 0 defines the role of the controller as a slave. After seeing the block diagram, let us again see the sequence of events in the service of the interrupt. Interrupts on input interrupt lines IR0 to IR7 are stored in the interrupt request register as logic bits. The priority resolver reads the contents of interrupt request register, interrupt mask register and in service register. The priority resolver resolves the priority and generates the interrupt request through the int terminal of the control logic. The int terminal interrupts the microprocessor through INTR. The microprocessor responds by sending the acknowledgement to 8259A. On receiving the acknowledgement, 8259A sets the corresponding bit in the ISR and resets it in the interrupt request register, indicating the acceptance of the request. 8259A also sends the opcode of the call instruction to the microprocessor. The microprocessor sends 2 more acknowledged signals to read second and third bytes of the call instruction from 8259A as the address vector of the interrupt service routine. The the microprocessor branches to the ISR specified by the address vector. After the microprocessor has completed the servicing of interrupt service routine, it has to inform the controller accordingly. The microprocessor informs the controller about it by sending an end of interrupt command. This end of interrupt command can be a specific end of interrupt command, or it can be a non-specific end of interrupt command. If the microprocessor sends the specific end of interrupt command, then the controller sets a bit in service register corresponding to the interrupt mentioned. But if it is a non-specific end of interrupt command, the microprocessor has not mentioned any interrupt, the controller resets a bit in ISR corresponding to the interrupt of highest priority among the ones being serviced. If the things have to be simpler, then an automatic end of interrupt command can also be generated. We can program the controller for this generation of the automatic end of interrupt command. Now, here we have seen various end of interrupt commands being generated. Now, let us see the various priority arbitration modes of the controller. This chip has versatile priority arbitration modes. They are fully nested mode, then automatic rotation mode, specific rotation mode, simple mask mode, special mask mode, the polled mode. Let us take up the fully nested mode. In this mode, the interrupts are given the fixed priority. IR0 has the highest priority and IR7 has the lowest priority. If there are frequent interrupts being generated, then the devices connected to the lower priority interrupts may get unsatisfactory service. In that case, other modes can be helpful. Like in case of automatic rotation mode, whatever is the initial assignment of the priorities, whenever any interrupt is serviced, that interrupt is automatically given the lowest priority, and the next interrupt given is given the highest priority. For example, if the initial assignment is that IR0 has the highest priority and IR7 has the lowest priority, and if IR2 and IR3 happen to occur simultaneously, IR2 having the higher priority will be serviced first. After it is serviced, it will automatically be given the lowest priority, and IR3 will be given the highest priority. Now, IR3 is still pending. Once this is serviced, IR3 will be given the lowest priority and IR4 will be given the highest priority. A slight variation of this is the specific rotation mode. In this case, any time during the execution of the program, any interrupt can be assigned the lowest priority, so that the next interrupt has the highest priority. For example, again, if the IR0 is given the highest priority initially and IR7 has the lowest priority, then during the execution of the program, any time, say IR3 is given the lowest priority through specific rotation mode, IR3 will be given the lowest priority and IR4 will automatically be given the highest priority. Now, if after some time IR6 is given the lowest priority, then IR7 will be given the highest priority. Next priority mode is the simple mask mode. In this case, the microprocessor writes a mask byte into the interrupt mask register. Wherever logic 1 is written, the corresponding interrupt is masked, and wherever logic 0 is written, that interrupt is unmasked. So, by masking the higher priority interrupts, we can change the priority order of the interrupts. A variation of this is the special mask mode. In this case, even during the execution of an interrupt service routine, any of the interrupts can be masked. Once this interrupt is masked, all other unmasked interrupts become active and they can be serviced after this. Another mode of priorities is the polled mode. In this case, the priority arbitration is not done by the controller, rather the controller passes a status byte to the microprocessor. Bits 0 to 2 indicate the code of the highest priority level that is requesting the service. The most significant bit D7 indicates whether the interrupt is present or not. A logic 1 in the most significant bit indicates the presence of the interrupt, and a logic 0 indicates the absence of the interrupt. Thus, the microprocessor polls the controller rather than each peripheral. The polled command can be issued by the use of an operational command word. Now, ideally, the interrupt service routines need to be placed anywhere in the memory space independently, but this controller does not allow this. It allows the placement of this interrupt service routines at an interval of 4 or 8. That is, if we think that the interrupt service routine corresponding to IR0 is placed at a memory location F000H hexadecimal, then the address of ISR corresponding to IR1 will automatically be generated by the controller as F004 if we have used the interval of 4, and the address of ISR for IR2 will be F008H and so on. But if we use the interval of 8, then the addresses can be F000H, F008H, F010H hexadecimal equivalent to 16 and so on. So, we have to program the chip accordingly. Thus, given the address vector of the interrupt service routine corresponding to IR0 interrupt, the other addresses are automatically generated at the intervals of 4 or 8. So, in this case, we need to provide the address bits 815 to A8 and A7, A6 and A5. All other bits will automatically be generated by the controller. The systems with moderate complexity do not need large number of interrupts to be provided for the devices. In that case, the controller chip used as a single chip is good enough. But in the complex systems, of course, the cascading in the master-slave configuration has to be carried. Now, let us see the programming of the interrupt controller A259A. This needs initialization command words to initialize the controller. In all, there are 4 initialization command words: ICW 1, ICW 2, ICW 3 and ICW 4. The first 2 commands ICW 1 and ICW 2 are essential, whereas ICW 3 and ICW 4 are optional. Now, let us see the details of these command words. Let us first take ICW 1. This initialization command word defines different parameters of the controller. Like the least significant bit of this command decides whether ICW4 is needed or not. If this bit is at logic level 1, ICW4 is needed. If this is logic level 0, then ICW4 is not needed. Next bit D1 decides whether this chip is being configured as a single chip or in cascade. If this bit is 1, the chip is being used as a single chip. If this bit is 0, this chip is being used as cascade. Then the next bit D2 decides the interval among the various interrupt service routines. If this bit is at logic level 1, the interval is 4, and if it is 0, the interval is 8. Next bit D3 decides whether the interrupts used are the level triggered interrupts or they are the edge triggered interrupts. If this bit is at logic level 1, the interrupts are level triggered interrupts. If this bit is 0, then the interrupts are programmed as edge triggered interrupts. Bit D4 is at logic level 1 for the identification of ICW1. Next 3 bits D5, D6 and D7 provide the A5, A6 and A7 bits of the address vector of the interrupt service routines. ICW1 is loaded by keeping A0 at logic level 0. Next initialization command word is ICW2. This command word supplies the higher 8 bits of the address vector of the interrupt service routines. The next initialization command word is ICW3. This initialization command word is optional, of course. This is used in case the chips are being used in cascade, that is in the master slave configuration. The last initialization command word is ICW4. This again is an optional initialization command word. This defines the chip being used with a 16-bit microprocessor or with an 8-bit microprocessor. In addition, this allows the generation of the automatic end of interrupt. Now let us see the sequence of these initialization command words to be given to the controller for initialization. To initialize the controller, ICW1 is sent by the microprocessor to the controller, followed by ICW2. The information contained in ICW1 decides as to ICW4 is required or not. In case ICW4 is required, then ICW4 is supplied to the controller, otherwise the controller is ready to accept the interrupts. Let us consolidate the initialization process of the controller by taking an example. Suppose in this example we want to initialize the controller with ICW1 and ICW2 only. So that means ICW3 and ICW4 are not required. Now ICW1 and ICW2 can be developed like this. Now the different bits of this byte for ICW1 define the different functions of the controller. The least significant bit decides whether ICW4 is to be given for initialization or not. Since we decide that ICW4 is not to be given, so we put this bit as 0. The next bit decides whether the controller is to be used as a single chip or in cascade. Suppose we decide that we want to use the chip as a single chip. So then this bit is going to be 1. The next bit decides the interval between the different interrupt service routines. So if the interval is 4, then this bit will be 1. Suppose we decide that the interval will be 4, so we put this logic level 1 here. The next bit decides about the interrupts. Now if we put this logic level 1 here, then the interrupts act as level triggered interrupts. Now the next bit is logical 1, that is for the identification of ICW1, of course along with the value of A0. The next 3 bits give the value of A5, A6 and A7 bits of the address vector of different interrupt service routines. So, this binary value of the byte comes out to be 1 EH, that is hexadecimal. Now, ICW1 is passed on to the controller by keeping the value of A0 to be equal to 0. Similarly, ICW2 can be developed. Now, ICW2 passes on the higher byte of the address of the interrupt service routines. So, that means the bits here decide about the higher byte of the address. Suppose we put them as 1, 1, 1, 1, 0, 0, 0 and 0. Now, this binary value comes out to be equal to F0 in hexadecimal. Now, ICW2 is loaded into the controller by keeping A0 to be equal to 1. Now, suppose the address decoder for the controller decodes the address to be such that the addresses of the internal registers of controller are F0 when A0 is equal to 0 and F1 when the value of A0 is equal to 1. So, with this we can write a small program segment for the initialization of ICW1 and ICW2 into the controller. For that, we first load the ICW1 into the accumulator of the microprocessor. So, 1E is loaded into the accumulator here. Now, this is sent to the controller through the port F0, because here A0 has to be 0. Again, the second byte, that is ICW2, is brought into the accumulator, that is MVI A F0 H, and is sent to the controller at a port out F1 H, because for this A0 has to be equal to 1. So, with this small program segment of the microprocessor, we have initialized the controller with ICW1 and ICW2 in different operations defined in ICW1. In order to change the default conditions of the controller, operational command words are used. In all, there are 3 operational command words used in the controller: OCW1, OCW2 and OCW3. Now, OCW1 is used to mask and unmask the interrupts of the controller. Let us see the details of operational command word 1. Now, this operational command word 1 controls the masking of the interrupts of the controller. The microprocessor writes a mask byte into the interrupt mask register of the controller. Wherever a logic level 1 is written, that corresponding interrupt is masked, and wherever logic level 0 is written, the interrupt is unmasked. Now, let us see the second operational command word OCW2. This operational command word generates the specific and non-specific end of interrupt commands along with the various rotation modes. And the last operational command word OCW3 allows the reading of the status of the pending interrupts from interrupt request register and the in-service interrupts from in-service register. So, to conclude, after having discussed the handling of the multiple interrupts and the details of the interrupt controller 8259A, we should be in a position to handle multiple interrupts in a microprocessor based system of moderate complexity. Thank you.